already here, enter. Okay. Okay, Omar is here. Okay, so there are already 11 of you. Okay, so we start. So yeah, like I've mentioned before this, in the second semester, second half of the semester, we will look at the second law of thermodynamics. Okay, so just recap. First law of thermodynamics concerning the energy balance. Okay, energy balance equation. So now we are going to look at the second law of thermodynamics. Okay. Okay, introduction. Okay, one thing. Okay, if you have a cup of hot coffee in a room, within the room temperature, okay, the temperature will decrease. Okay, obviously, if we just leave our cup of hot coffee or hot chocolate, anything, okay, and we put it on a table in the room temperature, we just leave it like that, and throughout maybe after a few minutes or a few hours, the temperature of the hot coffee will decrease, right? Okay, but the question now is whether the same cup of hot coffee will receive back, okay, will receive back the heat from the environment, from the room, to reheat back, to reheat back the coffee. Okay, but can the same cup becomes any hotter in the room? Can the temperature of the cup increase back, without any electrical appliance, any other extra device to heat it, just naturally? Okay, the answer is obviously no, right? The hot coffee, the cup cannot be heated back, the temperature cannot increase naturally without anything power put apply on the cup. Okay, naturally the process cannot be reversed. Okay, so first thing, the temperature of the hot coffee will decrease. Okay, it's as if it dissipates the heat. Okay, dissipates the heat to the environment surrounding of the in the room. Okay, around the hot coffee cup. Okay, but the reverse process cannot occur without any extra appliances. Okay, the reverse process naturally cannot occur. Okay, the same cup cannot becomes any hotter. Okay, so before this, we have seen the first law of thermodynamics, which mentioned that the sum of the energy, the change of the energy is equal to the change of the internal energy, and here we only have heat energy lah. We don't have any work or potential energy, etc. So only heat. So Q is heat. Okay. Normally, if you write the first law of thermodynamics, the energy balance within the cup and its surrounding, okay, we will write it this way. Okay, U1, the internal energy, equals to the heat being absorbed or being leaving or entering the cup. Okay, so we will write obviously the equation like this: U1 minus U2, the change of the internal energy, equals to the heat. So if we have like this, U1 minus U2, it will mean that heat leaving the cup. Okay, because the U1, we expect U1, the initial internal energy at 0.1 initially is higher than at the end. Okay, internal energy 0.2. So means that the heat is leaving the cup. Okay, and we from the first law of thermodynamics, we will write also like this: U2 minus U1 equals to Q, which means that heat entering the cup, the internal energy at the end is higher. Okay, entering, giving the cup. But okay, sorry. Okay, But okay, we can write from the first law of thermodynamics, we can write both of these equation, but only the first equation is logic. Okay, means in reality, it is logic. It can be done. The heat leaving the cup. But the second equation, we can write the equation. The equation seems correct, but in reality, physically, this cannot happen. Okay, the heat cannot enter back the cup on itself. Okay, so the reverse process cannot occur. So this is in reality, this is wrong. Okay, you can write the equation mathematically, but physically it is wrong. Okay, so the reverse process cannot occur. Okay, so that's why here we need the second law of thermodynamics to explain this situation. Okay, so in actual case, heat can only leave the cup, not entering the cup. Okay, but first law of thermodynamics applies for both situations because first law of thermodynamics, it doesn't mention whether you can you couldn't write the from the opposite direction, kan? U2 minus U1 or U1 minus U2. With the first law of thermodynamics, both of the equation are correct. Okay, but in reality, we know in actual case the second one is not correct; it's wrong. So we need a second law to prevent the impossible to happen. Thus, we need a second law of thermodynamics. Okay, so for example, like this one, you have like a resistance. Okay, resistor. Okay, so a heat being given to the resistor to heat up the resistor, but the opposite way the process cannot be reversed occur. So the same as this one, you turn the shaft, rotated. Okay, so the heat is being given. Okay, enter in the to the shaft. Okay, so and then but the reverse process, the work cannot just be the work from the shaft cannot just be rejected to the chamber here. Okay. Okay, one way process occur in a certain direction and not in the reverse direction. Okay, so that's why we need the second law, because a certain process can only occur in one way, one direction, not the reverse. A process must satisfy both the first and second law of thermodynamics to proceed. Okay, so we need this second law. Okay, so what does this second law mention? The second law may be used to identify the direction of the process. So with this second law, we know we can identify the direction of the process, whether the heat is entering, absorbed, or rejected. Okay, so there are heat absorbed and heat rejection. Okay, so with the second law, we know whether the heat is being absorbed or rejected. Okay, the second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and the transformation of energy from one form to another with no regard to its quality. Okay. The second law provides necessary means to determine the quality as well as okay. So the point here is quality. Yeah. Okay, so the second law, because later on you will see that the second law will guide us to identify whether the process can be reversible or not. Okay, so this reversibility will help to identify the quality of the process. If the process can totally be reversible, so we can say that it has very high quality, kind of quality of energy. We are talking about quality of energy here. So if the process can be totally reversible, which is that is ideal case, okay, totally reversible. So so it has a very high amount of quality of energy, which is this second law will help us to identify this quality of energy. Okay, the second law of thermodynamics is also used in determining The theoretical limits for the performance of commonly used engineering systems such as heat engine and refrigerators, as well as predicting the degree of combustion of chemical reactions. Okay, so later on we will see some thermodynamic cycles, and some of them are concern the heat engine, heat pump and refrigerator. So by applying this second law, we will know the limit or the maximum efficiency performance of this engine, refrigerator, heat engine, heat pump. What is their highest maximum possible performance or efficiency? Okay, by applying the second law. Okay, we will see that later on. Okay, again, many process can occur in one direction only. However, the first law of thermodynamics allow the process to occur in both directions. Okay, so again, with only the first law, it's not enough. Okay, because first law is as if indicates to you that any process, every process can be reversed back, can occur in both ways. But it actually, in reality, a lot of process can only occur in one direction only. So that's why we need this second law to prevent the impossible. The process in another direction is prevented only by the second law of thermodynamics. So this second law will indicate us whether the process is irreversible or not. Okay, it can be done in the opposite direction or not. Okay, the second law is obtained through experimental evidence and not through mathematical derivation. So means that in reality, in actual case, we saw that this situation is impossible. So that's how we come up with this. We came up with this second law of thermodynamics to define the quality of the process, the quality of the energy. Okay, these are very important. Okay, actually all slides today is very important. So please focus. Okay, because it will determine your understanding of these other few chapters, the next chapters. Okay, so thermal energy reservoir. This is a notion that you have to know. Okay, thermal energy reservoir. Okay, or we call it as heat reservoir. Okay, what do we mean by heat reservoir or thermal reservoir? It's a hypothetical body that can absorb heat without any change in its temperature. It's normally is something that is big enough, okay, large enough that even though there's a change in its body, okay, it can absorb heat, but generally the temperature of the reservoir will not be affected. Okay, example of a heat reservoir or thermal reservoir, our atmosphere, and our ambient atmosphere can be one types of heat reservoir. Large bodies of water, lake, ocean, etc. A two-phase system, water vapor, can also be identified as a reservoir, and a furnace, like a combustion chamber, to burner, right? Okay, so we have two types of reservoir. Number one is what we call source, supplies heat. The heat source, the reservoir that acts as a heat source. Normally it will the function is to supply heat. For example, our sun, solar energy. Sun can be the heat source. Okay, thermal energy source. Sun is one type of heat reservoir, but the function is to supply heat. Okay, and sink, heat reservoir, thermal energy sink is the function is to absorb heat. Okay, for example, is our atmosphere or lake, ocean. Okay, large bodies of water. Okay, so that types of reservoir, it will absorb heat. Okay, so we have to have these two types of reservoir. One to supply heat, which is we call it as heat source. The second one is to absorb heat, which is what we call as heat sink. Okay, heat source, heat sink. Okay, So now, now a very simple basic thermodynamic cycle. Okay, even the jet engine cycle, aircraft engine cycle is based on this basic cycle. Okay, turbofan engine, turbojet engine that you saw, that you see for aircraft, is actually based on this basic thermodynamic cycle. So this is the basic cycle in order for us to produce power or anything. Okay, energy. Okay, so remember this four. This is the most basic one. Remember this four. Okay, so normally we will start with pump. Pump is for liquid, remember, and compressor is for gas, vapor, steam. Okay, compressor is for gas, vapor. So in turbofan, you don't see turbofan engine, aircraft engine, you don't see pump. You use compressor, but the function is the same, to compress, to increase the pressure. Okay, but pump is used in liquid, for liquid. I mean, the working fluid is liquid, because aircraft engine, the working fluid is air. Okay, so air, we use compressor. Okay, so here we start with pump. So we need to give energy, the work required for the pump to run and compress the working fluid inside water or air. Okay, we start with pump, increase pressure, increase temperature, and then the working fluid here is water. Okay, so water will goes into the boiler. Okay, and it will boil, evaporates or boil. Okay, boiler also is for liquid. If it's air, we will use evaporator, but the function is the same. Okay, to evaporate is to boil. Okay, the working fluid. Working fluid is what goes inside this four device. Okay. So in order to boil or in order to evaporate the working fluid, we need a energy source, a heat source, okay, given to the boiler, given to the combustion chamber. Okay, kena ada source lah untuk bakarkan dia ataupun untuk panaskan dia. Okay, so this heat source is the thermal reservoir that acts as a heat supply. Okay, heat source. So for example, a furnace, if you have a burner, something like that, to burn the boiler, so that the boiler can heat up, okay, the water inside. Okay, so here is the where we supply the heat to the boiler. Okay, so this is the first thermal energy reservoir. Okay, heat supply. Okay, and then we have turbine. Okay, turbine. Okay, turbine is opposite, the function is opposite of the pump, which is to expand. This is to compress, this is to expand again. Okay, because last time in my class, some students cannot answer this one. Okay, so pump, the function is to compress, increase pressure. Turbine is to expand, expansion, reduce pressure, reduce temperature. And by reducing pressure, and usually the temperature entering the turbine is at a high temperature. Okay, that's why we have a certain limit of maximum of temperature that a turbine can endure, can withstand. Okay, boleh bertahan lah, okay, supaya material dia tak rosak. Okay, so the turbine, this is so turbine with expansion. So by decreasing the pressure and temperature, the turbine can produce power output. Okay, this is the results that we want, the desired output from our whole system. Okay, desired output, we have we need this the energy that we are going to produce, the electricity or the mechanical work. This is our desired output, and then the working fluid will continue. We complete the cycle by entering a condenser. So condenser is opposite of the boiler. This is to evaporate, this is to condense. So just opposite the function. Okay, so condense. When it condense, it has to exchange heat, like just now, this one. Okay, boiler is a heat exchanger. Condenser put also types of heat exchanger. Both of them are types of heat exchanger. So boiler, it will change heat with the heat source. Heat source, for example, here from the furnace or from the solar energy. Okay, the heat source, it will change heat with the means that the boiler inside here we have water, so the water will change heat with the sun or the heat source lah. Okay, so here to condense, in order to condense, the water needs to exchange heat with another environment, another reservoir. So normally the reservoir will be our ambient, our atmosphere, or if we have a cooling water, or we reject heat to the lake, to the ocean. Okay, so this is the energy heat sink. Okay, that will act as the to exchange heat with the working fluid water inside the condenser. Okay, so Q out, heat will be rejected as waste. Okay. So this four is the main concept of the thermodynamic cycle. So you have W in, work required to compress water. So the work that we have to put, we say put to input to the pump or compressor, so that the pump or compressor can run and can compress the working fluid inside. And then the working fluid will be boiled or evaporates, okay, to a steam or to vapor in a boiler or evaporator, okay, and then turbine expansion, and then to complete the cycle, okay, this is a closed cycle. So to complete the cycle, we will finish with the condensation process. Okay, the heat will be rejected from steam in a condenser as waste. Okay, so the first law of thermodynamics. So from this basic thermodynamic cycle, so we have this first law of thermodynamics, the energy balance. Okay, so here we neglect the kinetic energy, potential energy, etc. So we only have work and Q, heat rejected and heat supply. Okay, so at the total energy input and total energy output, this is first law of thermodynamics. Okay, so so you have work input, you have Q input, work input, Q input equals to work output plus Q output, heat rejected. Okay, so we can calculate this way. So we can rearrange the first law, the energy balance. We can also write it this way: Q in minus Q out will be equals to W out minus W in. Okay, which is will equals to the what we call the net power output. Okay, so this is the net power output. The desired output resulting from this thermodynamic cycle. Okay. So remember this one. Okay, everyone. Any questions? This is the most important, one of the most important part of in thermodynamics. And aircraft engine also we apply this basic cycle. So the boiler will be replaced with combustion chamber. Okay, so the fuel and the air will burn inside the combustion chamber. And then the pump, compressor, turbine, all are the same for aircraft engine. Except that we don't have condenser. Okay, we will see that in next chapter, Brayton cycle. But the concept is the same as power plant here. Okay. Next, what is a heat engine? Okay, what do we call a heat engine? Okay, heat and work. Okay, we have seen this heat and work. Okay, converting work to other forms of energy, example heat, is easy, but to convert other forms of energy to work is not easy. Okay, so this relates with the second law just now. To reverse back the process is not easy. Okay, for example, shaft work gives internal energy to the water that leaves the water as heat. Okay, so if we rotate the shaft here, okay, we have a water here. Okay, if we rotate the shaft, okay, the work from the shaft will give internal energy to the water. Okay, will hit the when we rotate the shaft, okay, it will heat up the water a bit. Okay, the heat increase in the water is what we call internal energy. Okay, that leaves the water as heat. The water is being heated, the temperature of the water, kita kacau dia panas sikit. Okay, we rotates the shaft and the heat will increase. The temperature of the water will increase a bit. Okay, so means that from the shaft work, we transfer the shaft work. Work is also is energy. So the shaft work is being transferred to the water in terms of internal energy. So the internal energy of the water will gain heat, will increase. However, transferring heat into the water will not turn the shaft. Okay, however, we cannot reverse back the process. Okay, now that the water is has some sort of internal energy, the water has heat, it has internal energy, but the internal energy from the water cannot rotate, cannot be used to just simply rotates back the shaft, to work back the shaft, to turn the shaft. A device that use heat to create work is called a heat engine. So we need, since we cannot reverse back the process, the internal energy from the water cannot rotate back the shaft. So we need some sort of a device that can use this heat within the water to create work back to the shaft here, for example. Okay, so this is what we call this device that can use heat to create work is what we call a heat engine. Okay, this is where we come from. Okay, so we need a device that we call heat engine that can transfer the heat and create work. Okay, and create work means we can create electricity, we can create mechanical power. Okay, so now without this heat engine, this device, we cannot even create the electricity. We cannot create any mechanical power to run machine, etc. Because the heat cannot just simply being transferred to run the shaft or any other device. Okay, so we need heat engine. Okay, so the characteristic of the heat engine: receive heat from a high temperature reservoir, like I mentioned just now, high temperature reservoir or the source. Okay, the source can be solar energy, furnace, nuclear reactor, fuel burner, etc. Any source of renewable energy. That is the thermal high temperature source. Okay, thermal reservoir lah. Thermal reservoir, the heat source here. Okay, and the heat engine will receive energy from the heat source and convert part of the heat energy to use full work. So some part of the heat source received will be converted to use full work, net power output. Okay, but not all. Of course, not all. Not 100% of the heat source will be converted to useful work. That's why we have efficiency of the machine, of the engine. It has certain sort of efficiency. Okay, if it's 100%, which is impossible, the case means that all the heat source is being converted to useful work, net power output. Okay, but in reality, no. So we have some sort of efficiency. Okay, so some part of the heat source will be converted to useful work, electricity, mechanical power, etc. Okay, convert, and another part, another portion will be converted as waste heat, will be rejected. Okay, to low temperature sink. The second thermal reservoir that we call heat sink can be atmosphere or ambient or river, lake, ocean, or cooling water tower. Okay, so if we reject heat, we use the word reject waste heat. Okay, it means that this waste heat will not be used. Okay, means, for example, if we have a machine, an engine that is that only can work in 60% efficiency, 60%. So means that if the heat source from the furnace or from the solar energy is, for example, 100 watt, you have 100 watt of heat source, 100 joule of energy of the solar. Okay, so only 60% means only 60 watt will be converted of this solar energy will be converted to useful power work. Okay, another 40 watt will be rejected actually, will be wasted. Okay, that is the actual case. Not all the heat source will be used. Okay, it can be used. Normally the lower grade of energy or lower grade of temperature will be cannot the temperature is not high enough to be converted to work, so it will be rejected, it will be wasted. So it will rejected to low temperature sink, atmosphere, river, etc. So this is like a cycle. So a heat engine will operate like a cycle. So from high temperature source, receive heat, Q in, produce power, produce mechanical work, W net out, and heat being rejected, Q out. Okay, here we don't have the work input yet from the compressor, right? But here we can, if we want to assimilate with this cycle just now. So this is the boiler. We need a boiler here. We have a turbine that can produce power here, and we condenser to reject heat. Okay. How efficient is energy? Okay, this one I have mentioned just now. Efficiency used to describe the performance of a device. Heat engine is a device that does not work at 100% efficiency, of course. Okay, in reality, net work out is equal to the difference between heat in and heat out. Okay, net work out is this one. Net work output is equal to the heat in minus heat out. Okay, we can evaluate it this way, Q in minus Q out, so we have net output. Okay, net work out is equal to the difference between heat in and heat out. Okay, heat out can never be zero, okay, due to the efficiency. So there will always be some portion of a waste heat rejected, unless the engine is 100%, which is impossible. So there's always have to have some portion of heat being rejected. Okay, heat out cannot be zero, mean you have to have some sort of Q out to kena ada sikit. Okay, network out can never be equal to heat in. This is also the same, means that the performance is not ideal 100%. So the network output is not totally equal to the heat input. Not all of the heat source too can be converted to work output 100%. Okay. Again, about the efficiency, performance, thermal efficient. Okay, so in order to evaluate, to quantify the performance of an engine, we calculate this thermal efficiency, what we call thermal efficiency. Okay. But in proportion, next semester you will see another term of efficiency, which is a propulsive efficiency. That is for aircraft engine. But for normal power plant, we use the term thermal efficiency. Okay. So the definition for this thermal efficiency is the desire of output, the ratio of the desired output over required input. The ratio of the desire, what we actually want, over what we give. Okay, what we want and what we give as an input. Okay. For heat engine performance, so we call thermal efficiency. To evaluate the performance of a heat engine, we calculate this thermal efficiency. Thermal efficiency, okay, can also be written. So for a heat engine, our desired output will be the network output. We want this network output. This network output is what is the electricity, mechanical output, etc. So we want this. Our desired output will be the network output. Okay, desired output is the network output. For this is the general definition. Desired output. But for heat engine, the desired output is the network output. Okay, and the required input, what we need to input is the heat input. Okay, heat input, the heat source just now. Okay, if we need to burn the fuel, so how much the fuel we need to burn, Q in. Okay, if we need to use solar energy, how much the heat from the solar energy that we need to give. This is heat input. Okay, so we can write the thermal efficiency this way. Net power output, our desired output, that, or we can write what W out minus W in, means the W out what we produce from the turbine minus the power that that we use to run the compressor, the electricity, the fan, etc. Or we can also write it this way by using only Q in, Q out, if you know the value of Q out, Q in. Okay. So here we have example of two heat engine with different efficiency. Number one, the first one has 20% of efficiency. So means that if it has 100 kilojoule heat input, with 20% of efficiency, it can only produce work output 20 kilojoule. And the rest, which is 80 kilojoule, is being rejected to the ambient, to the heat sink. Okay, or the second one, the second heat engine, again with the same amount of heat input from the heat source. Okay, so 30 kilojoule is being produced as work output, and the rest, 70 kilojoule, will be rejected. Okay, with efficiency of 30%. Okay, normally heat pump, heat engine, it has efficiency of around only 50%, 50%. Normal conventional heat engine without renewable energy source, means if you use natural gas, boiler, etc. Okay, the conventional way, the efficiency is around 50% only. Okay. Questions? Can the waste heat be redirected to the boiler? Okay. Okay, so this is what what the scientist or researcher, even myself, I'm currently studying. Okay, so this question is actually what we are going researcher going trying to do. Okay, what I explained here today in this slide is the basic the theoretical part, the basic cycle. Yes, we keep doing research, okay, how to minimize this waste heat. Okay, so there are few methods. Some methods is that we reuse this waste heat, but we have to combine it with another thermodynamic cycle. So it's like a combined cycle. Okay, so we because this waste heat will be as if the source of heat for another cycle. So we instead of being totally rejected, we can reproduce, reuse this waste heat, but we need to add another extra cycle that to run to produce power, to produce work from this waste heat. So that is one method. Another other methods, example is that this one you will see in few chapters. We will add regenerator. We can add regenerator to the cycle. The basic cycle, just now that I show you, the four component: pump, boiler, turbine, and condenser. That is the basic one, basic to run a heat engine. Okay, so there are, if you see the commercial power plant, maybe you see extra device, there's extra component in the cycle, which is maybe you have a regenerator, preheater, reheater, intercooling. Okay, I think you have heard about this, all these words, right? So those are the extra component that we add to the basic cycle, basic for just now. We add to improve the performance, the efficiency of the thermodynamic cycle of the heat engine. Okay, so to answer Marwan's questions, okay, either one method we integrate it with another cycle, which is, it will become a combined cycle. we reuse this waste heat. Or other method is that for example we add regenerator to the basic cycle. So this regenerator will use the higher heat, the higher temperature of the heat in the cycle to reheat the working fluid inside the boiler or the combustion chamber. Okay, actually this one I will explain. I think you have this in next chapter or last chapter. Means we add extra device, extra component, reheater, regenerator, etc. to increase the performance, and we reuse back the heat from the higher source to reheat the working fluid from the lower source. Okay, ada regenerator. Mari tunjuk. Okay, regenerator cycle. Okay, if I can just show you the diagram. Okay, this one, for example, I just Google it. Okay. Okay, this one. Okay. Nampak ke? No. Okay lah. Okay, this one. Okay. Okay, so here, this one, this is the basic cycle just now. Compressor or pump, and hot heat exchanger, which is the boiler, right? Okay, and then turbine, expansion, and this is the condenser. Okay, these four is the basic cycle that I was talking about. And then in order to reuse to increase the performance, the thermal efficiency of the basic cycle, we one method is that we add a regenerator to the cycle. We use the heat from the higher, we reuse the heat because the heat exiting the turbine is at higher temperature source, high temperature compared to the heat after the compressor. Okay, 2 to 3 and 5 to 6. So we use the heat from here to heat up slightly the working fluid, the water or the air exiting the compressor. That is one way. Before it can be rejected it is rejected as waste heat. We use this heat to increase the temperature before the working fluid entering the boiler or evaporator or the combustion chamber. Okay. I hope I answer maybe briefly first your curiosity. Okay, but of course it needs extra. It will be in your other chapter. I'm not sure last few chapter or in propulsion chapter. Okay, means you have to add extra component to the thermodynamic cycle. Okay, so but all the methods like I mentioned, combined cycle or regenerator, reheat, intercooling, it has pro and cons. Okay, so depends on what is our aim, what is our desired output. Okay, so we have to choose wisely how to increase the efficiency, the performance of the engine, whether we want to add intercooler, whether we want to reheat, whether we want to add another combined cycle. Okay, this can be done, but depends on what is your aim, what is your desired output. Okay. Okay, Marai.
Okay, thank you, Doctor.
Okay. Okay. So thermal efficiency again. So this one. We have few equations, few different equation that depends on the parameter, the input that we have. We can use this one, the net power output over Q in, or we can use this one, 1 minus Q out over Q in, or we can just write, net output Q in minus Q out. So we can use this equation. Okay, this one. Okay, sometimes we write it, the heat source is from the higher temperature reservoir that we write as QH. Okay, higher temperature reservoir, and the heat sink is from lower temperature reservoir. Okay, so we write it as QL. Okay, the lower temperature reservoir has a temperature TL, T low. So the heat rejected is defined as QL. So we can also write it this way. Okay, the same equation. Okay, so even the most efficient heat engines reject almost 1/2 of the energy they receive as waste heat. So 1/2 means 50%. Okay, or around 45. This one 55 only 55 megajoule is being produced output. Another 45 is being rejected to the atmosphere. To complete the cycle, we need to have this the heat engine need to reject some sort of heat to the heat sink. Okay, can we save QR? This is your question. Can we save QR? Can we save the heat reject? In a steam power plant, the condenser is the device where large quantities of waste heat is rejected to rivers, lakes, or the atmosphere. Can we not just take the condenser out of the plant and save all that waste energy? So this kind of like the same question as Marwan just now. Can we just skip the condenser part, or the heat rejected part? Okay, and so that we cannot, so that we wouldn't, we will not reject the heat. We can save all the output power, right? Okay, the answer is of course no. Okay, a heat engine cycle cannot be completed without rejecting some heat to a low temperature sink. Okay, so to complete the cycle, to complete the process, it has to have the working fluid, air or water, need to exchange back the heat inside with another reservoir, which is here the heat sink. Okay, so every heat engine must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle, even under idealized conditions. Okay, in a steam power plant, the condenser is the device where large quantity of waste heat is rejected to river. Can we not just The answer is unfortunately a firm no, for the simple reason that without a heat rejection process in a condenser, the cycle cannot be completed. Example. Okay. Example, you don't have the condenser part, the heat rejected part, heat rejection. So after exiting the turbine expansion, right? Okay, example, you don't want to waste heat. Okay, you want to save, of course. Okay, the working fluid, air or water exiting the turbine, okay, it is at a high temperature. Okay, high temperature and high pressure. Okay, so if you don't have this heat sink, or if you don't have condenser, we still need the heat sink. Okay, if you don't have this process, the working fluid, the air, the water exiting the turbine cannot at high temperature, pressure and high pressure and temperature, it cannot be directly entering the pump, okay, the compressor, because normally the pump, the compressor, it will compress, it will increase pressure and temperature. If you already have a working fluid at high pressure and temperature here, and then you increase again directly, it cannot, means that the working fluid keeps going higher and higher. Okay, that is one thing. Another thing, okay, if you remember the diagram, the TS diagram, like a mountain that we have done previously. Okay, so the phase of the working fluid within the turbine is normally is in vapor type, okay, or dry vapor, right? Remember the cycle, the TS diagram you draw in your exam test, okay? It is in terms of dry vapor, okay? So very dry dry vapor. Okay, so cannot for water, it cannot enter the pump, because pump, the phase of the working fluid within the pump is in liquid. Okay, pump, it can compress liquid. Okay, so but the working fluid exiting the turbine is in vapor, air. Okay, so you cannot just we cannot just transfer from the work output to the pump. Okay, to complete to complete the cycle, we need to reject some portion of the heat to the heat sink. Okay, some energy by transferring to a low temperature reservoir in order to complete the cycle even under adverse conditions. All right. Okay. Second law of thermodynamics. Okay, so we have this guy Kevin Planck statement. Okay, for the second law. So what does this Kevin Planck say? It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay, so this is the same thing. He's trying to say that we need to reject heat to a lower temperature reservoir. You cannot just receive heat and then produce work like this. Receive heat, produce work. Receive heat means no Q out. Okay, no heat engine can have a thermal efficiency of 100%. Okay, so we need to reject heat. So the heat engine cannot run in 100% efficiency. Okay, a heat engine that violates the Kevin Planck statement of the second law. So this type of heat engine, if it exists, it violates the Kevin Planck statement. Okay. Okay. Refrigerator and heat pump. Okay. So, refrigerator and heat pump first. Okay. So, refrigerator and heat pump is a heat engine that works in opposite direction. Okay. Just now you see you saw evaporator or boiler as the heat source, right? Okay, at above, and the condenser is at below, reject heat. Here, for refrigerator and heat pump, it is reverse. Okay, the function is reverse. Okay, but we still have expansion process. We don't use turbine, but it's still an expansion process. We decrease pressure, temperature, and we have compressor to replace the pump. Okay, because we use air. The transfer of heat from a low temperature medium to a high temperature one requires special device that we call refrigerator. Okay, because refrigerator is opposite way. Okay, you transfer the heat from you transfer the heat from the low temperature medium reservoir to the high temperature. Instead of the heat engine just now, we use the heat source from the high temperature and transfer it to the lower heat sink, lower temperature. But refrigerator is the opposite, from the low temperature medium to a high temperature. Okay, so refrigerator, like heat engine, are cyclic device. It still work in a cycle. The working fluid used in the refrigeration cycle is called a refrigerant. So the working fluid inside the refrigerator, we call it as a refrigerant. Okay, if for heat engine, we call it as air, water just now. Okay, the working fluid for the normal heat engine, but the working fluid for refrigeration, we use the term refrigerant. Okay, the most frequently used refrigeration cycle is the vapor compression refrigeration cycle. There is one name, one type of refrigeration cycle, vapor compression. Okay, in a household refrigerator, the freezer compartment where heat is absorbed by the refrigerant serve as the evaporator. Okay, so if you have your fridge at your house, the evaporator is the your freezer. Okay, so because your freezer is the main object, the main function of of a refrigerator is to cool, right? To decrease temperature, to cool down, to cool your things inside. Okay, that is our desired output for a refrigerator. The function is to cool the process. Okay, so the freezer compartment where heat is absorbed, okay, by the refrigerant serve as the evaporator. This is your refrigerator space, and the coils usually behind the refrigerator. Behind the refrigerator, you have the coils, or air condition. Aircon also the same, works the same run with the same process. Okay, air conditioner. Okay, so you have coils which is that acts as a condenser. Okay, behind the refrigerator, behind your aircon. Okay, where heat is dissipated to the kitchen air, serve as the condenser. So our kitchen air, our air within our kitchen is our heat sink, our heat sink lah, thermal reservoir. Okay, for this refrigerator. Okay, so because the condenser within the refrigerator, the cause will reject heat, will dissipate heat to the surrounding, which is the kitchen lah, if you use the refrigerator. Okay, so that's how it works. Okay, here. So since refrigerator is a reverse opposite of the process of the normal heat engine, so it's actually the network power, instead of being produced, this is what we put as input, require input. Okay, so to evaluate the performance of the refrigerator and heat pump, we don't use thermal efficiency. Okay, like just now heat engine, normal heat engine, we calculate thermal efficiency. Okay, but for refrigerator and heat pump, we use the term coefficient of performance. Okay, kita tak calculate thermal efficiency, tapi kita calculate coefficient of performance, or we note it as COP. COP is coefficient of performance. Okay, so the definition is still the same. Desired output over required input. The thermal efficiency also the same, desired output over required input. Except that here for refrigerator, our desired output is what? We want the cold refrigerated space, the cold temperature. So that is our desired output for refrigerator or for air conditioner. Okay, our desired output is not the work produced, the electricity. No, our desired output is the cold refrigerated space. So the desired output this time is not the network output, net power output. It is the QL, the heat from the refrigerated space. Okay, but our required input this time is not the heat source. The required input is the net power input that we need to give to run the refrigerator. Okay, the electricity. Okay, the required input is the net input. Okay, net power here. Okay, so we can also write net power input as QH minus QL. Okay, so we can calculate the coefficient of performance this way or in this way. Okay, the objective of a refrigerator is to remove QL from the cool space. Okay, so to keep the freezer refrigerator at a lower temperature, we need to remove the heat. So this remove this heat remove is what we call QL, that is our desired output. Can the value of COP be greater than VT? Yes. Okay, that is why we don't use the same term as thermal efficiency, because thermal efficiency cannot be higher than 1. Okay, it cannot be higher than 1. It cannot be higher than 100%. Okay, it's always lower than 100%, lower than 1. If you write, it says 0 point something, right? Okay, but for coefficient of performance, it can be higher than 1. So that's why we use the term COP instead of efficiency in percentage. So coefficient of performance is not in term of percentage, bukan percentage. It's just a number, okay, a ratio number. Okay, so means that it can be greater than 1, means that our desired output sometimes is higher than our required input. Okay, so here, so this one is heat pump. Okay, heat pump also the same as refrigerator. Okay, so heat pump also works as the opposite of the heat engine. So you have the cold environment. So our cold environment, okay, for example, heat pump usually we use if you are living in outside Malaysia, we have winter season kan. So the environment outside, ambient, is our cold environment, the heat sink, okay, at lower temperature. And the hot, the higher temperature reservoir will be our house, indoor house, okay, the warm heated space, okay, supposedly higher than the outside environment, ambient, okay. So the objective of a heat pump is to supply heat to the indoor, to the warmer space, okay. That is the objective of a heat pump. Or if you use heat pump for water heat pump, shower, your shower, right? You shower, water heat pump. So your desired output is to produce or water to supply heat to the water, so that the water is warmer, so that you can shower. Okay, that is the objective of a heat pump. Okay, so the work supply to a heat pump is used to extract energy from the cold outdoors and carry it into the warm indoors. So we extract energy from the cold outdoor, the environment. Okay, for heater, imagine this is a heater. We extract the energy from the cold outdoor, for example, at 4 degrees Celsius outdoor in winter. So, and then we run the heat engine, the heat pump, okay, with the net input 2 kilojoule, and we can produce the warmer space, okay, give heat to the inside the house, okay. Okay, so the coefficient of performance for heat pump, HP heat pump. So again, the same definition, desired output over required input, but this time around, our desired output is the QH. Okay, how much the heat that we are going to supply to our house, that can be supplied by using the heat pump. How much heat is being created lah, okay, to supply to the indoor. And the required input is the net power input here. Okay, so we can also use this term or this definition to calculate the coefficient of performance of refrigerator and heat pump. Okay, so it is opposite of the heat engine, normal heat engine. Okay, so it can be higher than 1. When installed backward and air condition function as a heat pump. Okay. So refrigerator and heat pump is the function is opposite of each other also. Okay, most heat pump in operation today have a seasonally average coefficient of performance of 2 to 3. This is conventional heat pump. Their coefficient of performance around 2 to 3. Most existing heat pumps use the cold outside air as the heat source. Okay, so the environment outside. okay, will be the heat source to the heat pump, to the heater. In cold climates, their efficiency drops considerably when temperature are below the freezing point. Okay, so the lower the temperature means it has to work harder. Okay, the heat pump has to work extra to produce supply heat to the warmer space. So sometimes the efficiency drops. Okay, because the temperature outside drops. In such case, geothermal HP that use the ground as the heat source can be used. Okay, so in Malaysia we don't use this, but outside at certain country, we can use the geothermal. This is one type of renewable energy source, geothermal or ground source heat pump as the source to cover to supply the heat to the indoor space. Okay, we use another renewable energy which is geothermal heat pump. Okay, air conditioner is basically refrigerator whose refrigerated space is a room or building instead of the food compartment. So air condition, aircon also works the same function as refrigerator, except that the space here is not the food compartment, the freezer just now, but it is the room, the building that we want to cool. Okay, the COP of a refrigerator, decrease with decreasing refrigeration temperature. Okay, so if the refrigeration temperature decrease, so COP here decrease. Okay, therefore it is not economical to refrigerate to a lower temperature than needed. So we have a certain certain peak value of temperature that we need to refrigerate our freezer. Don't try to decrease the temperature of the refrigeration temperature, because otherwise you the same as the heat pump just now, otherwise you will use extra work, and the efficiency, the performance of the refrigerator will reduce. Okay, because it keeps on running it keeps on producing extra work to refrigerate the freezer, the food compartment, even though it is not needed to refrigerate until that lower temperature. So we need to just refrigerate it at enough temperature, not too low. Okay. Okay. Again, second law of another statement for the second law of thermodynamics. Just now, the Kelvin Planck statement, it says that the heat engine cannot be run 100%. Okay, so we need to reject heat. Okay, so the other one is Clausius statement. It is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to a higher temperature body. Kelvin Planck statement and Clausius statement are identical. If one statement is violated, the other statement will be violated too. Okay, so Clausius said that it is impossible that we can construct a device, a heat engine, that they can only produce they can only transfer the heat from lower temperature to a higher temperature without using any net power input or without producing any power output. Okay, so that is what causes means. So we do to operate the device in a cycle, it is not complete only if we have lower and higher temperature body. We need to have whether a net power input or net power output produced from the device heat engine. Okay. Okay, this is the proof that the violation of the capital statement leads to the violation of the closing statement. Okay, so okay, reversible and irreversible process. Okay, jangan. Can we take a break? Penat cakap. Okay, can we take a break around 10 minutes? Or 15 minutes, 15 minutes until 11 a.m. Okay, we take a break. Later on we'll continue. Okay, until 11. Pause kejap Okay, are you guys here? We continue. You guys here? Amirul Akmal, Zainul, Miza, Omar, Umi, Mutaman, Kartikan, Hafiq. Di sini lagi. Afiq ada. 3, 4, 5, 6, 7, 8, 9, 10, 10, 10. Okay, we continue more. Kena cepat. Sorry, there's a lot of information in this chapter. Okay, continue reversible and irreversible process. Okay, so okay, like I mentioned just now, second law of thermodynamics give you idea of whether the process can be reversed back or not. Okay, so I have to understand this concept of reversible and irreversible process. Okay, because later on you'll use second parameter, which is entropy. I will introduce to entropy next chapter, next week inshallah. Okay, so reversible and irreversible process. So what is reversible process? Reverse, a process that can be reversed without leaving any trace on the surroundings. So this is the ideal process, ideal process, which is in actual case, in reality, is almost impossible. Okay, reverse process. An irreversible process, a process that is not reversible. Okay, so normally we will assume first, in ideal case, we will make assumption we will assume that the process is reversible, even though we know that in actual, in reality, it is impossible, but we will assume first that a process is reversible so that we can know what is the maximum performance of the process, what is the maximum power or maximum energy that the process can produce if it's work if it's reversible, means if it's ideal. Okay, so that's why it's also, even though irreversible process is impossible in reality, but we have to assume this, we have to know this also. Okay, all the process occurring in nature are irreversible. Why are we interested in irreversible process? Why? They are easy to analyze. Of course, it is easier. It means that we assume that all goes correctly. Okay, nothing went wrong. Okay, they serve as idealized model theoretically, means to which actual process can be compared. Okay, so we can compare this like a reference baseline. Okay, so how much if it's without any any apa tu faktor luaran, external factor, how much the maximum limit that the model can the process can produce work, can produce power, can work. Okay, some process are more irreversible than others. Okay, so depends. Some process has a very high irreversibility, some has lower irreversibility. We try to approximate reversible process. Okay, so we even though we know that the process is impossible that it is reversible, but we try to assume and we try to approximate it as we can. Okay, of course, because we want to reduce the loss. Okay, if it's irreversible, it has to it must has some sort of loss of energy. Okay. Okay, for example, reversible process, reversible for example, if you have a frictionless pendulum, pendulum tu apa nama, landul tengok benda. Okay, sorry, I cannot remember the word in Malay, pendulum. We have learned it in primary school. Okay, frictionless pendulum, if we throw the pendulum, if it's frictionless, no friction, so the process is reversible. The pendulum can return back to its initial location, initial point, right? If it's frictionless, but normally there is some sort of friction from air environment that can push or slower down the movement of the pendulum, right? So in reality, actually it is not totally reversible. But if we assume it's frictionless, so we assume that the pendulum can return back to its initial position. Second one, quasi equilibrium expansion and compression of a gas. If we slow down, if we compress or if we expand the piston, the gas within the piston slowly, very slowly, we might achieve a reversible process. Okay, means that there is very, very slight small change in within the gas from the initial state to the at the end state. If we if we do it very, very slowly, the compression and expansion, we try to maintain the behavior, okay, the energy within the gas, okay. But normally we just do it normal, so it is not a reversible process. Okay, so if the process is fast, it is normally irreversible, cannot be reversed back. If you do it slowly, we might achieve a reversible process. Okay, so we minimize the loss as much as possible during the expansion or compression. Okay. Next, okay, factors of irreversible process. What are the factors? What might okay, what might happen? Okay, the factors that can leads to irreversible process. Okay, first, the slow expansion or compression of a gas in device with friction. Okay, even though if we do a slowly expansion and compression process of the gas in the piston, but if the piston has some sort of friction, there is still some energy loss, means the process is still irreversible. Okay, so means that it's very unlikely to achieve a reversible process, ideal process. There's lots of other factors. Okay, energy is used to overcome the friction, where the energy is lost as heat to surrounding. So you lost some energy to the surrounding, you lost some energy that due to the friction. Okay, friction also exists between fluid and solid and fluid molecules, between the molecules inside the gas of the piston. Fast or unrestrained expansion or compression without friction. Okay, this time around without friction, but the process is too fast. Okay, it's too fast. So it might leads to irreversible process. Heat transfer through a finite temperature difference. Okay, finite temperature means the temperature difference of the process is too large, too big. So if it's only change in a very, very small temperature, small difference in temperature, then we might achieve a reversible process. Okay, for example, the soda here, if the change an irreversible heat transfer process, okay, because the change in temperature of the soda is what we call finite, is a bit large. Okay, finite, we can infinite is we cannot really define it. So it is an irreversible heat transfer process. If it's only a very, very small, slightly change in temperature, then maybe we can consider it as a reversible process. Okay. This one I skip, just another definition of reversible process. Okay. This one more important. Okay. So we have seen heat engine. We have seen the reverse cycle of the heat engine, which is refrigerator and heat pump. Okay, I repeat, we have seen just now cycle of heat engine, the main cycle of the heat engine. So the heat engine, what is the function of the heat engine is to give heat to produce work output from the heat of the engine. Okay, from the heat nak bagi transfer balik kepada work, produce power output, to transform the heat from the working fluid, water, air, in order to produce work output, the shaft power just now. And then we have the reverse heat engine, which is refrigerator and heat pump. Okay, now, okay, we have another theory, which is what we call Okay, Carnot cycle. This is actually French engineers, and since I learn French, also it's actually pronounced as Carnot cycle. You can just pronounce Carnot cycle. Okay, Carnot cycle as a heat engine or an ideal engine. Okay, what is this Carnot cycle or Carnot cycle? It is an ideal engine. Okay, ideal heat engine. Even though it is impossible, but like we mentioned just now, why we need to assume a reversible process, ideal process, easy to analyze, and we want to know the theoretical limit. Okay, so this is for a process, simple process two reversible, so the ideal. Okay, but here for the whole engine, or whole heat engine, um, if you want to assume that the ideal heat engine is the heat engine is ideal, 100% efficiency. Actually not exactly 100% efficient, but the ideal case it can become. Okay, so we have this theory of Carnot cycle. So Carnot cycle is the theory of ideal heat engine. So if we assume totally ideal process of the heat engine, okay, so we apply this Carnot cycle to the heat engine. So what is the actual maximum efficiency that actually the heat engine can produce actual power? Okay, why we must have an ideal device? A heat engine has an efficiency of less than 100%. What is the maximum efficiency it can achieve? We don't know. Right. A heat engine, we know that the heat engine cannot be 100%. Okay, the efficiency. But what is the maximum that it can withstand, it can sustain, it can produce the maximum possible? Even though it is not 100%, but the Carnot cycle is not 100%, but it is the maximum that we estimate the power of the heat engine. Okay, what is the maximum? So in order to know, to identify the maximum possible value of performance of the heat engine, we use this concept of Carnot cycle. The maximum efficiency is achieved by an ideal device using a Carnot cycle. So it was proposed by French engineer Sadi Carnot in 1824. Okay. The Carnot cycle, it has it's composed of 4 reversible process. Of course, if you want to assume ideal cycle, then we need this to assume that the process throughout the cycle are reversible. Oh, Tianshan, you just get me because we have other. Oh, you are the one that messaged me yesterday, kan?
Yes, doktor. Baru
Okay.
balik.
Okay. Nanti you catch up sebab macam banyak jugalah hari ni. Okay, this is the second part of the chapter. Okay.
Baik, doktor. Terima kasih.
Okay. Okay, so Carnot cycle, if we want to assume an ideal heat engine, so we have to assume that all the process, the 4 process just now, the boiler, compressor, pump, turbine, condenser just now, right? 4 process. We have to assume that the 4 process are reversible. Okay, because we want to consider an ideal heat engine, which is Carnot cycle. Okay, so first one. Okay, 1 to 2. Process 1 to 2 is we assume as isothermal expansion. Okay, isothermal expansion. Isothermal means constant temperature. Okay, the process only 1 to 2, not the whole cycle. 1 to 2, we assume that the temperature is constant. Okay, so isothermal expansion. Expansion decrease pressure like a turbine. Okay, but the process is but in the conventional heat engine just now, the expansion process in the turbine, you decrease pressure, you decrease temperature. But here for Carnot cycle, you decrease pressure, expansion, but we assume a constant temperature throughout the expansion process, isothermal. Okay, work done on the surrounding. So we produce work. Okay, second one, number 2, second process, 2 to 3, adiabatic expansion. Okay, what is adiabatic? Again, adiabatic means that we assume that the process um, no heat transfer within the outside of the system. We inside the system there is still heat transfer, but outside to the surrounding there is no, we assume there is no heat transfer, means the heat is conserved just within the system, within the piston, etc. Okay, so adiabatic expansion, system temperature reduced through heat transfer. Okay, there is still heat transfer, but just within the closed system that we consider. Adiabatic expansion. Okay, and then 3 to 4, isothermal compression, compress at constant temperature, gas pressure reduced. And 4 to 1, to complete the cycle, we have adiabatic, again, adiabatic compression, compress at adiabatic process. Okay, no heat transfer to the outside of the system. Okay, temperature and pressure increase and complete the cycle. Okay, I post it. Okay, so this 4 process consists for Carnot cycle. Okay, ideal heat engine. Okay, ideal engine for process, we have isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Okay, it's slightly different than the basic heat engine just now. Okay, so we can sketch the process of the Carnot cycle in a PV diagram, pressure versus volume, not velocity, volume. Okay, because in PV diagram we have also isothermal lines to indicate the isothermal lines here, isothermal process. Okay, so first one, 1 to 2, expansion. So expansion reduce pressure. So you have to decrease pressure. Pressure has to decrease from 1 to 2, decreasing pressure, expansion. Okay, but at constant temperature, isothermal. So this is the isothermal line inside the PV diagram. Okay, TH at higher temperature source, TH is constant, 1 to 2, T2 is equal to T1, isothermal. And with heat input, okay, we have heat input here, heat source. And then 2 to 3, adiabatic expansion here, 2 to 3, adiabatic expansion, still expansion, so still decreasing pressure, but this time around the temperature also decreasing from the high temperature to lower temperature. Okay, is not constant anymore. Okay, and then 3 to 4, isothermal compression. Now we compress. So compress, we increase back the pressure. When we compress something, if we compress air within the piston, okay, of course we decrease the volume. So volume decrease. If we expand, so the volume increase. So that's why we sketch it this way, not this way. Okay, so compress, volume decrease. Compress tekan, so volume dalam air tu dia kurang. Okay, so this sepatutnya this way lah. Okay, and then 4 to 1, to complete the cycle, adiabatic compression. Okay, compress, so increase pressure, automatically will increase the volume. And then and the temperature, this time around the temperature change from lower temperature to higher temperature. So this is the 4 reversible process, ideal of a ideal heat engine that we call Carnot cycle. Okay, ideal heat engine Carnot cycle use these 4 process. Okay, reverse Carnot cycle. Okay, just now we have heat engine and we have reverse heat engine. The reverse heat engine is refrigerator and heat pump, right? So for ideal heat engine, we also we have this Carnot cycle. So we have reverse Carnot cycle. Okay, again, heat engine, reverse heat engine is refrigerator and heat pump. Carnot cycle is the ideal heat engine. So the ideal reverse heat engine is this reverse Carnot cycle. Okay. So refrigerator and heat pump also has ideal engine lah. Okay, so a heat engine cycle where reverse becomes a refrigerator and heat pump. Okay, so the same for reversible process. This time around, we reverse the process, the cycle. So we start with 122 adiabatic expansion. We start with expansion. Just that this time around, we start with adiabatic, and then isothermal expansion. Okay, 2 to 3 isothermal expansion, and then adiabatic compression 3 to 4, and 4 to 1 isothermal compression. Isothermal compression to finish the cycle. Okay. Okay, just now from QH to QL. This one from QL to QH. Okay. Reverse cycle lah, reverse cycle, refrigerator, heat pump. Okay, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one, of course. Okay, sebab irreversible is the actual case. Reversible usually is the ideal case. So irreversible will have less efficiency, of course, because we take into consideration the friction, the difference of the temperature, etc. The efficiency of our reversible heat engine operating between the same two reservoirs are the same. Okay, because it only depends on the heat, high temperature source and lower temperature source. So as long as the high and lower temperature are the same reservoir, the same source, so the efficiency will be the same because it only depends on the heat source and the heat sink. Okay. Thermodynamic temperature scale, saya sikit juga ni. Okay, we can use to calculate the efficiency, the coefficient of performance. Either we use the ratio of Q, mean the heat Q in joule over Q also his hot and lower temperature. We can directly use the value of the temperature without calculating the Q, because if you want to calculate heat, we need mass flow rate. Okay. But if we assume that only one, the mass flow is constant, only one mass flow, only one working fluid, so we can directly calculate TH minus TH over TL using the temperature scale. Not all but some process we can directly calculate, use the temperature to calculate the efficiency. Okay, like this. Okay, the Carnot heat engine. Okay, okay, any heat engine just now. Okay, this is the previously we saw from the first part of the chapter. Previously we saw any heat engine, the thermal efficiency is 1 minus QL, the heat from the lower temperature reservoir to higher temperature reservoir, over a higher temperature reservoir. Okay, for Carnot heat engine, we can use directly the value of the temperature. We can still use this one also, but it's simpler, more simple, easier to use directly the temperature. You don't need to calculate the Q heat. Just for Carnot heat engine, okay? Just for Carnot, not for the normal heat engine. For Carnot heat engine, you can use directly the value of the temperature. Okay, so if the thermal efficiency is lower, the thermal efficiency of the heat engine is lower than the reversible, the Carnot efficiency. If this one is lower than this one, which is obviously means that the process is irreversible heat engine. Okay, if it's the same, then it is reversible heat engine, ideal case. Okay, means the heat engine can achieve the same amount of efficiency as the Carnot, the ideal case. So the heat engine is what we call reversible heat engine, ideal case. If it's this heat engine, the actual case is higher than the Carnot heat engine, this is impossible. Okay, because the Carnot heat engine give you the highest possible theoretical limit. Okay, so it cannot be the actual case cannot be higher than the what Carnot estimate. Okay. Okay, the quality of energy. Okay. So coefficient, okay, for refrigerator and heat pump, as usual, we use coefficient of performance. We don't use thermal efficiency. We use coefficient of performance. So the same method just now. Okay, this is for any refrigerator or heat pump. Previously, okay, but with Carnot refrigerator or heat pump, we can directly use the value of temperature. Okay, to calculate the coefficient of performance for heat pump and for reversible refrigerator. Okay, I think that's all. 11:30, nearly 11:30. I think we can do one or two simple exercise, example. Okay, to evaluate our understanding of this chapter. We do one, two exercise, example. Okay, so first one. Heat is transferred to a heat engine from a furnace, like a burner, at a rate of 80 megawatt. Okay, 80 megawatt. Watt is actually joule per second. 80 megajoule per second. If the rate of waste heat rejection to a nearby river is 50 megawatt, so the heat is being rejected, Q out 50 megawatt, determine the net power output and the thermal efficiency for this heat engine. So we know here the heat source is 80 megawatt, heat input QH, and the heat rejected QL is 50 megawatt. So determine the net power output, okay, and the thermal efficiency. It's very easy. Okay, so since we have instead of having the value of the network power output or network power input, the work output or work input, we know the heat input and output. So we use this heat input output instead of work output input. Okay, so net power output is Q in minus Q out. Kan? This one. If you don't remember, this is from this awal tadi tu. Okay, we want to calculate the net power output. So Q in minus Q out. So 80 megajoule minus 50 megajoule. So 30 megajoule directly. So senang je. So 50 megajoule, 30 megajoule, 80 minus 50. Okay, 30 megawatt, megajoule per second or megawatt power. So that is the net power output and the thermal efficiency. So thermal efficiency, you can use the heat input output juga. Okay, 1 minus QH minus QL over QH. 1 minus QL over QH. So 1 minus 50 over 80. Senang je ni. Okay. Yeah. Okay. So net power output just now, QH minus QL, or Q in minus QL. So we have 30 megawatt. And then thermal efficiency, since we have the value of heat input output, so we use this one, 1 minus QL over QH. Okay, so you calculate lah. 1 minus QL just now 50 over 80. Okay. So Marwan, you have 0.375. Okay. Okay, finish for that one. Okay. So next, second one, the food compartment of a refrigerator is maintained at 4 degrees Celsius. Okay, this is refrigerator. 4 degrees Celsius by removing heat from it at a rate of 360 kilojoule per minute. So you have to change the unit. Kilojoule per minute means removing heat. So QL. Okay, so QL 360. We remove the heat. And that is our desired output. If the required power input to the refrigerator is 2 kilowatt, okay, the net input W in 2 kilowatt, determine the COP of the refrigerator. Okay, coefficient of performance, remember coefficient of performance definition, desired output over required input. So desired output is the QL 360, but you have to change the unit to divide by the power input, which is 2 kilowatt. So you have the coefficient of performance of the refrigerator. Next one, B, the rate of heat rejection to the room that houses the refrigerator. QH. So we have to determine the QH. The QH, the heat rejected to the kitchen, to the room. Okay. Okay, Tian Shen, you can follow so far? By looking at the example?
Not quite, but I try.
Okay, tak apa. Okay. Okay, yeah, you have to understand first the cycle tu. Tak apa, just look at the ni. Okay, so the second one is also easy. Second. So apa tu? First, COP, coefficient of performance. So COP of the refrigerator. So COP desired output over required input. So desired output is the heat, the remove heat from the freezer, food compartment, the freezer kan. The food compartment freezer tu we remove heat, QL. Okay, this is our desired output because the function, the objective of a refrigerator is to maintain the cool space kan, the freezer kan. So that is our desired output of the refrigerator. Okay, so we remove heat to the from the food compartment, the freezer tu, to the surrounding. Okay, so that is QL over required input. So the net input given to run the refrigerator. Okay, so QL is 360 kilojoule per minute. So minute, so you have to divide with 60 kan. Okay. Kan 1 minit. Okay. 300 minit. Okay, and W net is 2 kilowatt. 2 kilowatt. So okay, kilojoule per second, kilojoule. Okay, betul. Okay. Okay. So 360 ni. Okay, so 3. Okay, so the coefficient of performance 3. Okay, remember coefficient of performance can be higher than 1. Thermal efficiency cannot be higher than 1, but coefficient of performance can. Okay, second one, B. Second one, the rate of heat rejection to the room that house the refrigerator, the kitchen or the environment within the surrounding our refrigerator. So means that we want QH. Okay, QH ni because it's in rate per second, so we have to have notation atas tu. Okay, So from the definition of the cycle, tengok balik refrigerator. Okay, this one. Okay. So QH is the sum of the QL, the desired output, plus the required input, the W net in. Okay. So we want to calculate this QH. So just the sum, add the W net with the plus QL. Okay. So W net in plus QL. Okay, so you have this one 360 divided by 60 just now 6 kan? 6 plus 2, so 8 kilowatt lah, or kilojoule per second. 8 tu kasi kira 400 kilo watt. Okay, kilojoule per second 40 bagi 6. Betul lah. Okay. Okay. That is for the second one. If we still have time, so maybe we can proceed with the third question. We have time. 11:37. Okay. Okay, everyone. Until now, first question and second question, everyone understand? Except maybe tension. The others? Any
Yes,
question? Afiq, okay?
Okay, Doktor.
Amirul, Akmal, okay? Eugene, Umi, Khairul Rushdi, Marwan. Number 1, number 2, no questions?
Okay, Doktor. Faham lah.
Okay. Okay, number 3. A Carnot heat engine receives 500 kilojoule of heat per cycle. Okay, from a high temperature source at 652 degrees Celsius and rejects heat to a low temperature sink at 30 degrees Celsius. Okay, this is Carnot heat engine. Determine the thermal efficiency of this Carnot engine, the amount of heat rejected to the sink per cycle. Okay, so remember, a Carnot heat engine, even though it is an ideal heat engine, it doesn't mean that it has totally 100% efficiency. Okay, it's still not 100% efficiency, even though it is an ideal heat engine. It just gives us an idea of the theoretical limit, the maximum efficiency or the maximum power that the heat engine can produce. Okay. Saya nafas. Okay. A Carnot heat engine. Okay. Receive 500 kilojoule of heat per cycle from a high temperature source. So QH 500. Okay. At 652. Okay. The TH is 652. Reject heat to a low temperature sink at 30 degrees Celsius. TL is 30 degrees Celsius. Okay, so determine the thermal efficiency of this Carnot. So we can use directly the value of the temperature. No need to calculate the the T, the H, the Q, okay, the heat tu, kita boleh guna, since it is a Carnot cycle, we can use directly the value of the temperature. So number 3, thermal efficiency. Okay, thermal efficiency of the reversible or Carnot. Okay, it is 1 minus, just now if for normal heat engine we have a QL over QH kan. So Carnot heat engine we can use directly the temperature. Okay, TL over TH. Okay, we can just leave it in terms of since it is a ratio, we can leave it in terms of degree Celsius. Tak kisah pun. Kejap. Rasa value. No. You have to change it into Kelvin because you are dividing. Nanti cuba ni lain. Okay. Okay, so 30 degree plus 273. Kalau minus, if you subtract, then you don't need to change the ni. Tapi yang ni takut silap. Okay. 1 minus 30 plus 273, change into Kelvin. Heat source 652. Okay. Okay, so this is the thermal efficiency. Second one, the amount of heat rejected to the sink per cycle. Okay, the amount of heat rejected to the sink per cycle. Okay. So QL Okay, so for this one, for this question B, we can use the, since we have the value of QH 500 kilojoule, and we have the value of temperature, we will use this one. This one, okay? This one is temperature scale, okay? This relation of ratio of Q heat equals to the ratio of the temperature. Because we have QH, we have TH, TL, we want to search for QL. Only for Carnot reversible, we can use this one. Okay. So, QL is QH TL over TH. Okay, QH TL over TH. So QH just now 500 500 and TLTH this one lah, 30 plus 652 plus okay. So okay, so you have the QL reversible around 164 kilojoule, the heat rejected. Okay, heat rejected QL, the amount of rejected to the sink per cycle is 164 kilojoule. Okay. Okay, the last question you try to do by your own self concerning the heat pump. Okay, before we finish, I would like to give you an assignment. Okay, we are already in week 11. Okay. Nafas. Okay. Okay, mana tadi? So this one. Okay. Okay, before this, at the beginning of our semester, I mentioned to you that your evaluation, your assessment will be, of course, 40% final exam, and then 20% your test one. You have already know your marks. 20% final exam. Another 40%. Okay. Actually, I was thinking of giving you two kind of like a small assignment like the homework previously, two homework, so it will be accounted for 10 plus 10, so become 20%. And this project is only accounted for 20, and this last project is only accounted for another 20%. So 20 tests, 20 small assignment like homework individually, and another 20 this group project or team project. I mean two member in a team project. Okay, 20%. But since we have to cancel our class, etc., 2 weeks, so we don't have much time. So I have to change the slightly a bit the assessment marks. Okay, so okay, test 20% finish, and the homework assignment that you have submitted will account for 10%. Okay, like I have mentioned previously. Just that this project, instead of giving you another homework plus this project, I will only give you this project. So no more other homework. But this project will be accounted for 30%. I have to increase a bit the portion. Instead of previously 20, I have to increase to 30 because I'm not giving you another homework anymore. Okay? Faham tu? Understand tak? Okay, so this is 30%. So, but the task actually I didn't change. From even though previously I have prepared these slides for the project to be accounted for only 20%. But now I'm increasing, but I still give you kind of like the same amount of tasks. Okay. So okay. For this project, I'm not sure whether because some students prefer to, even though the task is big, they still prefer to do it individually because you're doing online and sometimes you don't meet your friend, so it's harder to do a teamwork. And or maybe some to minimize to your workload, you prefer to do in group or partner. Okay, because you are not too many, only 13 of you. So if you want, if you don't want to do individually, you can do in two with your another partner, 2 students. Okay, so I will give you freedom to choose whether you want to do this individually. Maybe the workload is extra, but the benefit is that you can do the assignment by yourself. You don't need to bother the others. Okay, or if you want to divide the workload, you can do with another friend. So only 2, maximum only 2 person in one group. No more than 2. Okay, so I'll give you choice to choose. Okay, option to choose whether you want to do it individually or you want to do with another friend. Okay, the marks is the same, Okay, still 30%. Whether individually or by with a partner. Okay, so project also is about so we just learned this. It's about air source heat pump or refrigerator. You can choose. Okay. Okay, a project overview. Okay, the application can be used in mechanical, aerospace, and urban energy system. Each student will develop the mathematical model of the system, design thermodynamic cycle, simulate the cycle, and implement the energy balance. Okay, so the objective is that, okay, of course, you have to have the mathematical model, the thermodynamic model, the equation, the energy balance of the cycle that you are proposing. Okay. And you have to, of course, sketch the schematic diagram of the cycle. Where is your boiler, your evaporator, your turbine, etc. and sketch also the thermodynamic diagram, TS diagram or PV diagram, and explain the process. Okay, and then simulate the cycle. Okay, this part I will explain in the next slides. And lastly, you have to calculate the energy balance, means and the performance. Calculate the heat input, calculate the thermal efficiency, calculate the AR or the COP, coefficient of performance. Okay, the net power produced, etc. Okay, so I have divided into 5 tasks, 5 small tasks to guide you what to do. Okay, but in the end, you just have to submit the report, and you have to present. Okay, so in the end, you present and you submit report. But I divide the task into 5 different tasks to guide you what to do. Okay, so first one, okay, accounted for around 5%. Of course, you have to read a bit the background literature on the thermodynamic model of an exhaust heat pump. So there are several different model of exhaust heat pump. Okay, the basic model, or sometimes the what we call as a modified model, like I mentioned to Marwan just now. If we add regenerator to the cycle, we add reheat to the cycle, we add into another heat exchanger to the cycle. So different model has different thermodynamic mathematical energy balance dia lah. Okay, investigate application of exhaust heat pump refrigerator in different energy systems and choose one thermodynamic model from literature for this project. So you, from your literature reading, okay, you search a bit background study of these different exhaust heat pump or refrigerator. You choose. So you have several types. So you study the pro and cons according to you. Okay, you analyze the literature. You analyze the literature and what are the pro and cons of different system, and finally you choose which one you want to apply. Okay, so you do literature review and summarize a bit your literature review, maybe around 2-3 pages. Okay, and some background study of or maximum 5 pages background study of different heat pump exist, or different refrigerator or air conditioner exist. Okay, by using different heat source. Ada yang guna solar, okay, ada yang guna natural gas. Okay, so study different types. Okay, and then choose which one you want to apply. Okay, and then second task, develop the thermodynamic cycle and create a numerical model with parameters given in literature as input. Okay, so this one, I think you have learned computer programming. I'm not sure whether you have used MATLAB or Python. I think Python, is it, with Dr. Yazdi or Dr. Sharil, right? So you know a bit about that. So you have to use that. Okay, but only simple, not too. I mean, simple programming, not too complicated one. Okay, because you want to solve the thermodynamic cycle. Okay, you have to key in. Okay, build the mathematical model using the MATLAB or the Python or any other computer programming software that you are familiar with. You can use. Okay, and use it to create the mathematical model, and then from there you can calculate the performance of the cycle. Okay, the thermal efficiency, the power, etc. just now. Okay, and then but write the mathematical model, write it in the report. Okay, include in the report, and then that mathematical model you have to create it in the software MATLAB. Okay, and then task number 3. Okay, still concerning the numerical model we have created. Okay, I want to because you have to compare the results that you get from your MATLAB or from the Python. You get the results, right? But you want to reduce your because there will be some assumption that you have to make. you have to assume some parameters. Some parameters are given in the literature, some are not given. You have to assume. For example, the density of water we know. Sometimes there are parameters that we have to assume. So in order to minimize the error of your assumption, of your hypothesis, you need to run the cycle, the program, the loop several times, right, in the MATLAB, in the Python. So you have to reduce this percentage of error. Okay, I give here around 20%, but if you get less than 20% is better, less than 10% or okay, means that you compare the result that you get from your numerical model with the literature review, okay, with the baseline reference, your reference. Okay, so but try to reduce the error as much as possible. Means that sometimes you have to do the loop, kan? Loop tu you have to run several times. Okay, and then plot the TS diagram of the cycle. So once you get the results, you plot the TS diagram of the result. So you have the temperature of each of the location, temperature after the compressor, temperature after the turbine. So you use that to plot the diagram by using the MATLAB or by using just Excel. So and then so you get the result and you analyze the result in the report, in your report. And then actually this part is the same juga. Analyze, examine the error, include the analysis, so discuss, etc. And finally, last one, okay, so week 14, 27th of November. Okay, so initially I plan for you to present during class. So since we have limited time to finish our syllabus content, okay, so you I will not ask you to present live during class, but you record your presentation. Okay, record your presentation and submit to me with the written report. Okay, written report, submit to me. So deadline is the week 14, 27th January, before your study week. Okay, that final week, week 14. So you have like 4 weeks more lah. Okay, so you record video and submit the report, the written report. No need to present during the class. I have to cancel that idea because you don't have enough time to cover the content, the other content. Okay. Any questions? Any question from the floor? Semua okay? How many of you prefer to do individually? Ada yang prefer buat seorang-seorang ke? Okay, initially I suggest this project is a teamwork lah, but because I know is the workload is quite heavy because you need to write report and you need to search for data, run, etc. So me myself, I advise you to do with another friend. Okay, but if some of you find it difficult, because I know with this online study, you sometimes your friend is not being cooperative, so you prefer to do it alone. So it's up to you, but the marks is the same whether you do it alone or with your friend lah. Okay, any questions? Okay, if no question, then we finish here. Okay, 11:59. Okay, no question, I finish here. I will upload the slides, etc. Stop recording.